Hello, welcome back. In this lecture, which is titled The Mathematics of Manipulating the Truth, we're going to learn this topic called the Gaussian Elimination. Yeah. Ideally, at this point, you've already learned how basic vector and matrix operations work, and you would need to know that in order for you to understand this topic. So, I'm Professor Wu. Let's get started. So here's a problem. Why don't you take a second and look at this problem that you probably have seen in the SAT? All right. Basically, this type of problem is the kind of problem that Gaussian elimination is good at solving. Let's look at how we would solve this traditionally. So a concert charges $20 for adult and $10 for student. So it tells us that the concert sold 100 tickets. That means that if we let A be the number of tickets sold for adults and S for the number of tickets for students, right? So we have the adults sold a certain amount and the students sold a certain amount of tickets. What we know is that the total number of tickets is 100, implying that the total number of adults and students, if you add up all the ticket number, is equal to 100. The next thing we know is that, well, $20 for adult and $10 for student, and they made $2,000. So if you have 20 times the number of adults plus 10 times the number of students, that's the total amount of money we made. So it's adding up however money you made from adults and students. So basically, now what we have is two equations and two unknowns. We call these kind of equations linear system of equations or just linear system. So this is like a linear system of equations. And with these, you probably learn from algebra, right? You can solve these kind of equations when you have um, two equations and two unknowns. So in high school, you probably learned this that you can solve this through substitution. And basically, we have two equations, right? Let's look at the first equation. Well, we can convert this first equation by solving for a. So this means that if we have a, move the s here, minus s. So we now know that a can be represented in terms of s. And all we have to do now is plug this a into this equation to get rid of a, right? If we plug it in to a, we end up getting here, right? This used to be a. So now notice all we have is s. And if we solve for s, we know that s is equal to 0. If we know s is 0, then a must equal to 100. So this is essentially how you would solve it with like whatever you learn in high school. And this makes sense if you have two equations or three equations with three unknowns. But what happens if we have a much, much, much bigger problem? For example, let's look at this one, right? You have 10 equations and 10 unknowns. And this becomes really burdensome to solve if you try to substitute them all together. So, a new approach to solve large equations like this was emerged, and it is called the Gaussian elimination. The point of Gaussian elimination is to make solving this less burdensome. I mean, it's still a lot of work if you're trying to solve it by hand, but it's less work compared to if you're trying to do the Gaussian, to do a substitution for every one of these. So, what is Gaussian elimination? Well, in essence, Gaussian elimination is about the manipulation of truth into a different truth. So you go from one truth to a different truth that happens to be more useful. I mean, this is not the same as lying. Manipulating the truth into another truth, you're still stating truth. You're not like making things up randomly. So basically, if I tell you something, you can come up with definite conclusions and that those conclusions could be quite useful. I mean, let's just look at an example. For example, let's say we have start with this true statement, right? This is something you were told that it has to be true. Well, if this is a true statement, notice that if we subtract both sides by 2, so we minus 2 here and minus 2 on both sides, right? This gives us a new statement, and it's essentially says that x is equal to 2. So we have two statements, the original one and a second true statement. You can tell which one is more useful, right? Hopefully you come to the conclusion that this is more useful than this one. So by manipulating the original truth, we arrive to a different truth, and certain truths are more useful than others. So basically, Gaussian elimination is a way for us to manipulate like the system of equations that allows us to reveal the final solution. Okay, so the natural question is like, okay, we can manipulate these equations. How do we go about doing them? Well, there are three main ways to manipulate the equations. Okay, the three ways of manipulating the truth. Let's look at the very first way. The first method is actually really obvious. If you look at the statement I give you, like 2 cups of sugar allows you to make one cake, right? So from this statement, it also implies that if we have 4 cups of sugar, therefore we must be able to make 2 cakes, right? So from this statement, we can get a different statement, but equally true. Equally true. In fact, notice that we can essentially multiply any number here. Any number here. Let's say you have 5, and if you multiply 5 here, so it's saying 10 cups of cake will give you 5 cakes, right? So you can multiply by any number n. Any number n right here. And the statement will still be true. And this tells us that if we convert these into equations, such as 2x1 plus x2 equals to 1, well, we can manipulate this equation as well, simply by multiplying by any number. So if you have 2, right? So if you put 2 here, 2x1 plus x2 is equal to 2, right? So the first method of manipulation is essentially that if you have an equation like this, if you multiply the same number on both sides, like 7, 7, the equation is still equivalent, right? The truth is still true. Let's say we have 2 equations. So let's say instead of just one, we have 2, and we assume these 2 equations to be true, which we define here. Equation 1, equation 2. We're going to call equation 1 E1, stands for equation 1. We're going to call equation 2 E2, stands for E2, equation 2. Now, if we multiply both sides of equation 1 by 2, so we multiply 2 here and 2 here, then we're going to get a different equation, right? So we multiply by 2 on both sides. So we started from this statement, which was assumed to be true. We ended up with a different statement. So even though the two statements looks different, they're actually saying the same thing. They provide the same information. And we're going to symbolically represent this transformation, right, as 2E1. Because we took equation 1 and then we multiply by 2, right? So what we did is, so this action of manipulation, we're going to define it as 2 times the first equation. Okay, so this observation basically allows us to make the very first conclusion. And the conclusion is that if you multiply or divide, multiplication of some true statement on both sides, then you get another true statement. Okay, so you have equation something for x equals to 3 x, right? If you multiply some number both sides, the equivalence is still the same. All right, now if we continue with this logic, then here's our original statement. And then what we did is that we took equation 1 and multiplied by 2, and we say that's the new equation 1. So we transform equation 1. So notice we go from equation 1 to the new equation 1, which all we did is multiply by 2. So instead of just transformation of one particular equation, now we have transformation of an entire system. So this is a system of equations, and now we transform to a new system of equations, a new statement of truth. And and the two of them are actually equivalent, okay, equally true. Okay, now the key you want to notice is that we start with some statement, and then this is some kind of action. And the way we define action is, here's the equation. What did we do with the equation that results in the new equation 1? Okay, that's what this notation is telling you. So our first conclusion tells us that we can create a new true statement by multiplying any number on both sides, right? So, and the way you want to think of Gaussian elimination, basically we do a series of these transitions. Like we go from one set of statement to another one, to another one, to another one, and eventually we reach a final one that allows us to come up with like really useful conclusions. And okay, now let's look at the second method. The second method of manipulation is that, let's say we're given again this same, exactly the same linear system, and we want to flip the order. So E1 becomes E2 and E2 becomes E1. The way we represent this action is that we say, well, E1 and E2, they essentially swap spots. So the second way of manipulation says that if you were to swap the order of the equation, notice how this went here and this went here. If you swap the order of the equations, it's still a true statement. So if you say dog equals white is white and cat is equal to black. Now, if you were to swap these two statements, cat equals black, dog is white, right? It would not influence the validity of these statements. So this is also pretty obvious. You can just swap equations and change the order of them. And we symbolically represent the swap this way. So, second conclusion is that if we change the order of the statements, it won't impact the validity of the statements. All right, the third method basically says that we can combine equations together. So now we have two equations. If we were to add up these two equations, then the result of the addition or subtraction creates another true statement. So over here you have 2x1 x2 1. So 2x1 x2 1. So that's the equation. And then we're going to add the bottom one, which is 0x1. Notice how it doesn't have x1 here. Minus x2 right here is equal to 1. So if we combine the combination of these two equations, says that 2x1 is equal to 2 right here. So we went from this, and then we created another true statement. Well, this transition can be written as, this is our original statement. And then if we were to add the first equation, the second equation, and set that to be our first equation again, we will get something that looks like this. right here. So notice how the combination became the first equation, like such. This leads us to the third and final conclusion, which says that the summation or subtraction between two true statements yields another true statement. So you can also combine them and then to create a new true statement. And essentially, the action is defined using these notation. All right, so if you just think about these three manipulation methods, right? You can multiply by both sides, you can swap them, you can combine them together. They seem pretty obvious, right? They seem pretty obvious. However, if you combine these operations together, it allows us to solve an entire system of equations. So previously, remember we added them together, right? So this is the original statement. Now, if we added E1 and E2 together, what do we have? Well, we got this statement, right? We did that previously. We add this, and this is the same. So that's from adding E1 and E2 together. So after this action, we went from this statement to this statement. And then notice if we simply take E1 minus E2 and set that to E2. So what is E1, E2? E1 minus E2 and set that to E2, you will get this equation. Right? You can see that from here. E1 minus E2. And we end up getting this equation as the new E2. Okay, so now as a final step, we now have this. What happens if we divide E1 first equation by half? We divide it by half and set that to be the new E1. Or if we divide it by 2, right? Then essentially we get x1 is equal to 1. And then what I do is I multiply E2 by -1. So we end up getting this statement. And the key to realize is that this statement, x1 plus 0x2, is equivalent to x1 equals to 1. And this is like the main reveal, is that we basically started with this system of equations, and by transitioning each time, we're able to reach the actual solution itself. Like at this point, we know exactly what x1 and x2 are. And basically what you need to do is to take a moment and realize what just happened. Right? What just happened was that by manipulating the system of equations to create, we're able to reach the final solution. Now, this technique works for any size of the problem. And this is great. And the goal is you want to manipulate the equations such that both upper and lower triangular are 0. So notice this is the upper triangle, this is the lower triangle, and the diagonal should equal to 1. And this makes sense because if these are 0, it means that x1 must equal to 3, right? x2 must equal to 2, x3 must equal to 1, so on and so forth. So your goal is to keep manipulating the equations so that you can reach this, what we call the RREF form, reduced row echelon form, RREF, where the upper triangles are all 0 and the lower triangles are all 0, and the constants in the diagonal are always 1s. So the process of basically doing the transitions so that you eventually reach this step is called the Gaussian elimination. Okay? So that's basically the point of Gaussian elimination. And the general idea is kind of makes sense, but it takes a lot of practice to do it. So at this point, why don't you try yourself? Okay, let's say you have this two simple basic equations, and what you want to do is see if you can use do Gaussian uh, elimination, and see if you can reach a point where the upper triangle is at zero and the lower triangle is at also zero. At which point you would know the solution of this equation. Okay, so pause the video and see if you can do it. All right, over here is the solution. You can pause the video and take a quick look. Hopefully, you're able to get this. Okay. All right. So now that you get the idea of Gaussian elimination, well, if you have to write this x1, x2, x1, x2 every time, it gets really cumbersome because, well, we're just repeating the same thing. So notice that when we do Gaussian elimination, maybe we can just get rid of this. Right? Instead, we can write a shorthand. Notice that this system of equation can be written into matrix vector multiplication is equal to 2, 1, right? 2, 1. This means that all we really care about is the numbers. We don't really care about x1 and x2 because why do we need to copy them over and over again? So, so, so anyway, so what I'm saying is that instead of writing the equation and the transitions this way, it's most of the time Gaussian elimination. What we do is we just assume this is there and focus on the numbers. And we call this the augmented matrix. So we basically look at the equation and create the augmented matrix. And from this, performing Gaussian elimination, we don't need to copy x1 and x2 over and over again. So over here, for example, we perform Gaussian elimination. We basically take half of E1 plus E2, right, and give that to E1. And then we take E1 minus E2, so this one minus this, which give us a new E2. And as a result, we now know exactly what the solution is. Now this same idea applies even if we have a much larger problem, like such. If we have a much larger problem. And then what we do is we take this larger problem, convert it into an augmented matrix, and then little by little, we reach the reduced row echelon form, RREF. Okay? And again, your goal is to get all the bottom and all the top triangles to be zero. Okay, so now, given that we have a larger equation, it seems to me that it's not clear how we can convert the original matrix into this REF form where the upper and the lower triangles are zero. Okay, so there are actually steps to do this. The easiest way is basically you want to view this problem as a box. And what you do is you basically want the top left of the box to equal to 1. So you try to manipulate equation so that one of them is equal to 1. Notice that if this is equal to 1, it's very easy to get the rest of them to be 0 because 1 times minus 3 we'll get rid of 3. 1 times minus 1 will give us 1. So we can easily, once we have the first value at the top left as 1, we can easily zero them out. Once you achieve this, what we do is we shrink the box, and now we want this to be 1, right? And then once this is 1, we remove all of the values below. So notice how it gives us all zeros. Okay? And then finally, we have zeros here, and then we want to set the very last one, top left of the box, to be 1. And this basically will give us very close to the reduced row echelon form. Right? If you can achieve the bottom triangle, this is called a row echelon form, REF. But once you're in REF, you're pretty close to reduced row echelon form. And you basically repeat this until you just basically start with a big box, get all the zeros, smaller box, get all the zeros, and even smaller box, get all the zeros, so on and so forth. All right, well, once you have achieved row echelon form, which is when the bottoms are all zero, you want to go from row echelon form to the reduced row echelon form. And you can use the exact same idea. If you know the 1 here, you can basically use this one to zero them out. So 1 times 5.5, so adding them together will cause the 0. 1 times 3 would zero this out, and 1 times minus 1. So you basically set 1, zero them out, set 1, zero them out, set 1, zero them out, get the 1 here. Then you zero these out, and zero these out. And that will give you the reduced row echelon form. Once you obtain the row echelon form, right, you could technically solve the problem, because if you know that this is x1, x2, x3, x4, so this right here is x4. It's basically telling you that x4 is equal to 2. Now, if you know that this is x3, x4, and you know x4, you can get x3. So once you reach row echelon form, it's actually pretty easy to solve. But the standard way is reduce row echelon form. You know, you can I can talk all day, and there's a lot of intricacies. So it actually just makes more sense that why don't you pause, think through what we are talking about, like think through what we're talking about, and then see if you can try this yourself. Okay, like how do we convert basically this into an augmented matrix? So that's the first thing we want to do. What is an augmented matrix? Well, augmented matrix is a matrix where we get rid of x1, x2, x3. And then from the augmented matrix, we want to reach this thing called a reduced row echelon form. Yeah, I think the best way is just try it. If you don't get it, we'll have somebody, the TAs, to come help you. Um, if you are watching this at home, if you don't get it, then I recommend you go through the logic one more time. And if you still don't get it, definitely come and ask me or the TA. The solution to the previous problem is right here. Yeah. All right. So once you have found the solution, so you do the whole transition of true statements into the final statement, and you now know what x1, x2, x3 is. So you now know these numbers. Well, are you able to double check if you got the right answer? Yes, you can, because this right here is equivalent to 1, 0, 3, 2, 1, 0, 2, 4, 1 times x1, x2, x3 is equal to 7, 2, 4. Right? So if you found the solution, it implies that you know what x1, x2, x3. So you can double check if they're correct, because if you multiply this vector, which you found, by this matrix, you should be able to get this vector here. Okay? And if they match, it means you did it correctly. If they don't match, it means you did it wrong. So, like I can give you the idea, but at the end of the day, you just need to practice. You until you can do it, you try yourself. You don't really know how to do it. So just give it a try again, right? Again, write it into an augmented matrix, like, and then make sure you scale the very top one to one, and then zero them out, and the next one to be one, and then zero them out. Okay, so give this a try. Pause the video. Now, I yeah, yeah, if you have the solution, you should be able to plug it in and test it out. Okay, so these are big equations, right? And if you're trying to solve this at work, you probably would not want to be solving like thousands of variables by hand. What makes more sense is that you should realize that with NumPy, you are able to achieve the solution pretty easily. Okay. Now with NumPy, remember that we're able to define a matrix as well as a vector. Once you define it, there's a you need to import a library of linear algebra, and you simply say solve, and it give you the solution. So basically, if you have this equation here, you convert it into the matrix A and the label Y, and after you solve it, you get the solution. So this is the solution for x1, x2, x3, x4. All right. Now, NumPy will give you the solution, but sometimes you want to actually know the RREF itself. And in those cases, you can try a different library called SymPy, and you can download SymPy this way. Okay. Once you download it, you can simply define the matrix that you want. Now, this is the augmented matrix, right? So there's technically a line, and you just call the matrix RREF, and you automatically solve the RREF for you. So you can at work, you if you're actually out working, this is the method you want to use. You don't want to solve it by hand. You should just have gone through Gaussian elimination, so you know the idea, but in practice, you don't want to solve it by hand. All right, here's another practice problem. I want you to solve this one by hand, and then you can confirm your solution with NumPy and SymPy. This is a pretty big problem, so it will take you a while to solve it. And the Python solution is right here. And over here is the solution to this problem. Like, you can pause the video and take a look if you don't have the slides, and the solution continues, which this should be your final answer. Okay. And lastly, ideally you are able to put this knowledge to work. So why don't you see if you can solve a word problem, right? If you can solve this problem, then it implies that you understand it and you can incorporate the knowledge into real life situations. And over here is the solution. Okay, you can take a look, see how it's solved. All right, so I think that's it for lecture 3. I will see you in the next lecture.